Okay, so but before we get started, what I want to do is say looking over this part of the book, I realize that this is the part of the book that I'm really not at all not so happy about. I think everything. So what we're going to be doing over the next couple of weeks is going through this through a certain kind of set of ideas, which they're kind of spread out over chapters like 14 through 17, and I think what I was trying to do in the book was actually relate to explain those ideas, and at the same time say quite a bit about their relation to geometry and to symplectic geometry. And I think in retrospect, I think that's probably a mistake, because if you've so some of you have studied some geometry and are used to this, then I think you'll find this interesting. But for most people, having this kind of slightly exotic geometry thrown at them in this way just makes the whole thing more confusing. So what I'm going to do is hopefully today I'll talk about some of the stuff that's in chapter 14 and about kind of how to think about classical mechanics in terms of Lie algebras, which I think is an interesting point of view. And then I'll jump forward and start talking a little bit about what's in chapter 16 about what's called the symplectic group. So we've so I'll begin perhaps by going over the stuff about the Heisenberg group from last time. But what I really want to try to get to today is just the beginnings of what's in chapter 16, and to talk about the symplectic group, and so how to kind of what that is and how to work with it is kind of what I really want to get to, and what's kind of behind the story. So let me talk about that, and then over the break, if we're all not supposed to travel and stay home, then you can do your best to try to make sense of some of these chapters, and we'll come back a week from today and Thursday, and I'll try to explain the rest of what's in chapter 16, and then go back and talk about what's the stuff that's in chapter 15, the more geometrical point of view. So I won't be so closely at all following what's in his notes, and if you're trying to follow them and you find that where I start going on about geometry and symplectic geometry, that things are getting kind of confusing, then that's probably normal. So do your best to kind of follow that stuff, but you'll find by the time you get to the end of chapter 16 that there's some very, very, very specific calculations, which are relatively straightforward manipulations of Poisson brackets and things, and those are the calculations I really kind of most wanted to get to, and you'll see that those are the things which you really need to do to solve the problems. And the next problem set's going to be due, a week and a half from now, not next Tuesday, but after that. Okay. So are there any questions about that? About that? Because if there are no questions right now, what I want to do is let me just kind of quickly or spend the first part of today going over the story about the Heisenberg Lie algebra and the Heisenberg Lie group, because that and what that's all about. And then so that'll be in some sense the anyway, I want to kind of get a solid idea of what that group is and what the representation of it is that we're dealing with. And then we'll move on to the story about another group, the symplectic group, and that's what will keep us busy then for a while. Okay. Okay, so let's get started. So last time what I did was, let's see what I did. So I think maybe to start with the point of view that physicists take. So if you see, this appears pretty much in every quantum book. At some point, there's something that's called physicists call canonical clinization. And what they mean by that really is that they've got the this says that you have operator. So this is going to be for some number of degrees of freedom. Let's call it so d degrees of freedom. Last time I mostly wrote down the formulas for d is equal to 1. Today I'll write them for arbitrary d, but that's not too difficult. And you should think, and one example would be, so d is equal to 3 is the particle in 3 spatial dimensions. But the idea is that the same formalism, the same kind of algebra, and the same representation, the same underlying mathematical structure, it would apply to other dimensions, but it's also going to apply, for instance, if you have multiple particles, you just kind of, instead of having d is equal to, if you have 2 particles, instead of having d is equal to 3, you'll have d is equal to 6. That for each particle, you've got 3 directions it can move, and so now you've got 6 degrees of freedom. So the formalism that we're going to develop here, works with an arbitrary number of degrees of freedom, and mostly what the simplest case is a single particle where d is equal to 3. But if you have n particles, it'll be 3n. Okay, but what this is all about is just that the let's see, that you've got a so you have operators. What canonical quantization means is that you've got operators qj, j, pj, where j is equal to 1 up to d. So there's d of them, and they satisfy commutation relations. pj is I h bar 1. Okay, but if you multiply, so if you operate first with this one, then with this one, and then you subtract the same thing in the opposite direction, you're going to get I times the identity operator times dimensional constant h bar. And so some of the time I'll keep h bar around. Sometimes I'll for simplicity I'll set it equal to 1, but depending on what I want to talk about. Okay, now in some sense what's going on here is that we'll see in a minute, is that what this structure is, that we want to think about the structure as being these operators are the operators that you get from a Lie algebra, representation of a Lie algebra called the Heisenberg Lie algebra. So I'll go over that in a minute, but you should think of it, these are basically the homomorphism relations saying that you have a representation. But the funny thing that's happening is that you're not actually, if you're just told this, you're not actually told any, you're not actually given a specific representation. You're not actually given, what do these operators act on? And so the one story about what they act on is that they act on, so you said you actually get a real representation by choosing a representation space, by act on your space is L2 RD. Okay. So they act on functions on d dimensions, and we'll often write these psi of Q1, Q2 up to QD, and these variables are called the configuration space variables, and for a single particle, they're just the spatial. Anyway, they're just the spatial coordinates. But if you've got several particles, they'll be the spatial coordinates of the different particles. Okay, and then you're given a specific. So you're given an actual representation of these operators on the space by setting Qj is equal to multiplication by Qj, J, and Pj is minus I h bar P Qj. Okay. And you can check that these things satisfy these commutation relations, and then this is your story. But the thing that should make you think that there's something a little bit more abstract going on than this is that there's another completely equivalent package of information, which is what happens if you Fourier transform. And instead of looking at functions of Q, you look at functions of the momentum variables of P. So, so this would be or H is equal to L2 of R D, where now they're now you've got functions, and here you're going to have your psi tildes of P1 up to PD, which are functions of a Fourier transform variable, which has an interpretation of being functions of the momenta, and then QJ, well then PJ is going to be multiplication by PJ, and QJ is then going to be I H bar D D PJ. Okay. So there's something more. So you have kind of two versions of the same thing, and these are related by the Fourier transform, which is a unitary isomorphism. So the Fourier transform gives you a map, gives you a unitary map between these kinds of functions, between this space, and between these kinds of functions, this space, and it preserves the standard Hermitian inner product on these spaces. So it's unitary, and it's actually, and if you work with L2 functions, then it's actually an isomorphism. For any one of these, you get one of these, and there's a one-to-one correspondence between these things if you set it up that way. And that's also true also if you work with Schwartz functions. You can't work with anyway, yeah, it's true if you work with Schwartz functions. Like I guess this is also true if you work with well anyway, this if you let me just say it, it's also true if you work with Schwartz functions. So this is the so what you've got is you've got this kind of algebraic structure, and you've got two different realizations of it as operators on a space, which are kind of the same thing up to a unitary transformation. And so these unitary transformations, the Fourier transform is a it's not like a unitary matrix because these are interdimensional spaces. So it's a linear transformation, but it can't really be written as a matrix because these are not finite-dimensional spaces. But it's just the standard story of what the Fourier transform is. Okay, so this is the standard package that comes with what we say is canonical quantization. But what I want to do is I want to kind of explain that there's a more abstract point of view on this. That what you've got in which these are just two different unitarily related examples of the same representation called the Schrödinger representation, and the and we can actually explain what the abstract story in the language of Lie algebras and Lie groups in a fairly simple way. So that's what I wanted. So that's what I want to do now is take this package and then just change language and say explain what Lie algebra and what Lie group this is a unitary representation of. Okay. But the thing to say, but this is kind of the fundamental thing which you do with it. I mean, the next. If you want to get physics out of this, then the next thing you have to do is to choose a Hamiltonian, like the Hamiltonian for a particle and a potential, and you want to get kind of more operators, more observables by taking by building some more complicated operators out of the Q's and P's, and that's so we'll develop some technology for doing that kind of next. Okay, so what's the if I want to argue that this is all about a Lie algebra representation, what's the Lie algebra and what's the Lie group? So maybe the simplest way to write down, well, one way to write down the Lie algebra. So this is going to be the Heisenberg Lie algebra. And I started writing it down for 1 degree of freedom last time, and I showed how to write it down in terms of matrices. But the kind of the simplest way to think about it is maybe just as some abstract, just to think about it in terms of as a vector space with a basis where the basis elements, the bracket is defined on the basis elements, and thus on the whole vector space. So what I want to do is I want to say that it's what it's going to be is going to be R. So it's going to be 2D. Where again, this is the D of the number of degrees of freedom, and then there's going to be an extra one with basis. So as a vector space, the Heisenberg Lie algebra is this guy, but you have to. But the point is that it has some non-trivial bracket relations on it, and so with the basis, so you choose a basis, big X J, big Y J. Again, J is equal to 1 D, and then an extra element Z, and Lie bracket. So the bracket, Lie bracket is defined on any vector in here by what it does on a basis. So it satisfies these relations. It's equal is Z. And okay, so one of the directions in here is distinguished, and that's why I write it this way. And that basis element commutes with all the others, commutes with everything. It's called central. It's called central in the language of mathematicians. Something.
So what about the bracket for xj and xk or yj and yk?
Oh, those are always zero.
Okay.
Yeah. Oh, so sorry. Well here. Yeah. Sorry. Delta K. Yeah. You're right. I guess I should have said. Yeah. I think. Yeah. Thanks. I probably should have said that separately. You're right. X, J, xk. Yeah. Is equal to yj. Yeah. Thanks. Okay. Yeah, so the x's are commuting objects, the y's are commuting objects, and z is something that commutes with everything else. But there's this slightly non-commutative thing going on that's here. Okay. And so you should think of this as something that you can diagonalize the x's, and you can work with functions of the eigenvalues of the x's. That's your functions of your q's, or you can diagonalize the y's, and that's going to be functions of your p's. But you can't simultaneously diagonalize xj and yj because of this relation. Okay. So this is the Heisenberg Lie algebra. What else I want to say about it? Okay. So anyway, that's really all I want to say about it. You can also rewrite it. You can also rewrite it as a maybe let me just say this. So this is isomorphic to the Lie algebra of matrices of the form. So let's see, if you want so you take things that are 0 all the way down the diagonal and 0 on down here, and then you put z up here, and then you put the components of anyway. So when I'm writing small, okay, so an arbitrary element of the Lie algebra will be, you know, something times big Z plus something times some small xj times the big xj's plus some small yj times the big yj's. And so, and this will give you some vector. So there's some vector which is x small x1 up to xd and small y. Now let me actually small y1 up to yd, and then zeros in here. So if you have matrices that are kind of 0 everywhere except this part of the first line and this part of the last column, and then you can check that if you take the commutator of any two such matrices, you'll get the same commutation relations you would, you know, by if you expressed everything in terms of basis elements and use these relations. So this isn't necessarily so being able to use. I think the thing to say about what's going on here is that, you know, we're not going to be looking at matrix representations on finite dimensional vectors. So thinking of these things as matrices is not always that useful, because what we're going to do with this Lie algebra is we're going to realize it with operators on an infinite dimensional space. So thinking of this kind of matrix realization, I mean, you probably won't see this matrix realization of this algebra in a physics book because it's not actually that useful for what we're trying to do. It is useful, I think, maybe for keeping in mind, you know, if you're used to thinking about Lie groups and Lie algebras in terms of matrices, well, this is, you know, it's still just a matrix story. It's just a story about matrices. The problem is that it's a story about a certain matrix Lie group and a certain matrix Lie algebra, which are where the only interesting representation is going to be infinite dimensional. The representation on, you know, on d plus 2 dimensional vectors here is not actually is non-unitary and not an interesting representation. Okay, so another perhaps another reason for thinking about this is that you can motivate the definition of the Lie group. So you can ask, what's the Lie group whose Lie algebra is this? And using the definition of Lie algebra I was giving, it's going to be a group of matrices that is the group of matrices you get if you exponentiate these guys. Okay, but again, writing down and okay, so I'll tell you, that's the Heisenberg Lie group. So we'll take the Heisenberg group, and that this will give a name. When I'll write it as H with a subscript 2d plus 1. Okay. It is the corresponding group. And so you can think of it, if you want, you can think of it as the group of matrices you get by exponentiating the kinds of matrices I just erased. And what it is it's so as a space. So this is what it really is it's so as a space. So it's R 2d plus 1. But the thing about it is that it's not. It has a funny funny nonlinear group law. Okay. So and it turns out that if you Let me give you the. Okay, let me actually. So the standard way to to do calculations. The best way of kind of doing these calculations of these matrices and everything is to use the use what's called, well, there's the general formula called the Baker-Campbell-Hausdorff formula, called the CH formula. But let me say it this way. So a special case. And what I mean by this is just that this is true for matrices. It's also true in general for linear operators, that you have e to the, if you exponentiate some matrix or a linear operator in general, and then you multiply it by this guy, it turns out that what you get is something that's close to A plus B. So if these are commuting matrices, if these are commuting objects, or if they're just numbers, then you can then you're just going to get this. You're going to get the standard exponential relation. You find though that if these things don't commute, then you need a more complicated formula, and you can work out what the various ways of working out what the formula is. But it goes like this. AB. This is a next term, and then what happens? So this isn't. Anyway, then what happens is you get plus some higher order or commutators. So you get a bunch of higher order terms which are given by the by taking the not just a commutator of two objects, but the commutator of an object and a commutator and a commutator. So that's the general formula. And now the one nice thing about the Heisenberg group and the Heisenberg of the algebra. So these are guys in the Lie algebra. When you exponentiate them, you're getting guys in the Lie group. But what you can do, what you find in the Heisenberg Lie algebra, the only commutator that's non-zero is there are so these are equal to 0 for the Heisenberg case. The only non-zero commutator that you get is that one of x, j, y, k, and that commutator gives you something z, which commutes with everything. So if you start taking more commutators, you're always going to get 0. So what happens here is that you get just this. You just get this formula. Okay. So anyway, so you can. If you actually want to work out specifically the relationship between things in the Lie algebra and things in the Lie group, in the Heisenberg case, this formula really tells you exactly all you need. So at the level of this tells you, you're very close to a situation where you have a nice exponential group law, except that there's this funniness going on. And okay, and then another way of thinking about it, you can use this to show. Maybe instead of working with matrices, another way to work with the Heisenberg group is to use what are called exponential coordinates. So in other words, the same. So if xy, so label. Let me just say it this way. So you label g L of h 2d plus 1 by the coordinates, and so there's an x vector, a y vector, and a z in the Lie algebra. such that such that G is equal to exp of the exponential of this guy. So if you want to label it, the simplest way of kind of working with this whole story is to use the same coordinates on the Lie algebra and on the Lie group. And it's the same thing that you do if you're trying to think of the real numbers as an additive group. You know, you can think of the Lie algebra as R and the Lie group as R, and the exponentiation gives you an isomorphism between the two. So you might as well use the same coordinates on the two, and that's what's called exponential coordinates. So we're gonna I'm gonna think of elements of the Lie algebra as given by elements of this vector space, which are kind of pairs of vectors of d-dimensional, and one other real number. But I'm sometimes also going to say that these are the same, these same coordinates will also give you group elements in the Lie group, and you just get the group element you get by exponentiating this element of Lie algebra. And if you want to know how to do that, this is probably this relation will tell you how to do it, or you can go and write everything in terms of matrices and exponentiate the matrices by hand if you feel like it. Okay, and then I wrote down some formulas. Okay, anyway, then let me just leave that there. Then that you can actually, well, no, let me write it down. I guess I can. Yeah. Actually, let me not do that. I mean, so you can go in the book and find you can find the expression for the group law of written in exponential coordinates. It's not that it's fairly straightforward. It's not especially enlightening. Let me not do that. Okay. So now, but what I want to do. So that's pretty much the whole story. That's all there is to say about the Heisenberg Lie algebra and the Heisenberg Lie group. Also remember that physicists, often if they do talk about this group, they call it the Weil group. But now what about representations? Representation. So what about representations of this Lie group or this Lie algebra? And the so there's some basic theorems I won't really prove, but you can. And they essentially say this: there exists there exists only up to unitary equivalence. Actually, I don't want to say that. Up to unitary equivalence. Let me just state the theorem as just a single theorem. So the basic theorem is called the Stone-von Neumann theorem. It's a bit. It's a bit tricky to prove. It involves some tricky analysis if you try to prove it. But it's what the Stone-von-Neumann theorem says is there exists so up to unitary equivalence. There exists only one irreducible unitary representation of H2D plus 1. Okay, and it's the one you already know about, and it's the So let me write it. I'll write it as instead of pi, I'll write it as there's a gamma for Schrodinger, and it's called the and I'll call it the Schrodinger representation. And it is, so it's the thing which, you know, for elements of the Heisenberg group, you get operators that are acting on a representation space, and this representation space is infinite dimensional. This is not a matrix representation, and it's you might as well think of it as L2 of RD. Where okay, and so writing down so you can write down formulas for it in terms of the group, but typically you're interested in the Lie algebra version of the representation. So you're interested in what I call the corresponding derivative of this representation, which is where you put a prime here, where the Lie algebra representation is. Well, it's just gamma S prime. So on these x sub j's, these are on applied to psi, which of the q vector, you're going to get. Okay, so one reason I wrote these with a different symbol than q's is I want these to be skew adjoint. These should be skew adjoint operators, because they're the derivatives of unitary operators. So you take the qj and put it a minus I, psi, and that's just minus I qj psi q vector. Okay. And then on the yj's, you take minus I pj. So that's minus h bar d b qj. Okay, and then on the central element, is equal to again. So this is just going to give you the identity operator, but you have a minus I. Actually, let me think of it. Let's set h bar equal to 1 for now. So, but let me just think of this. Let me think of this a bit more abstractly. Where c psi of q, c is some real number. Okay. And I have to say something, to say this a little bit differently, is that the c appears here, is that up to unitary equivalence, there exists, let's say I have to put in something here that says for each c not equal to 0, I want a real number. Okay. So what this is really saying is that there's the Stone-Van-Orman theorem says that if you pick the way that the central element z acts, it has to act, by something skew adjoint, but by a constant. Then it once you've chosen that constant and if it's non-zero, then you just write down the standard thing you're used to. That gives you an infinite dimensional unitary representation of the Heisenberg Lie algebra. That the claim is that actually, that the exponentials of these operators all make perfectly good sense. You can see what those exponentials do, and you can see what the Heisenberg Lie group does, and this is it. So this is something. So you've already kind of seen this, and you have a lot of experience working with this, in this kind of physical interpretation as a wave functions of a particle. And it's going to turn out what's going to be interesting about this is we've already seen two different. We've seen that Fourier transform gives you another unitarily equivalent version of this representation, but there's also other ones which we'll come to later in the class. Okay, I think that's about all I want to say about this. Okay, so anyway, are there any questions about this? So it's kind of I've shown you a new Lie group and a new Lie algebra, and I've in some sense claimed that the representation theory of this is actually, in a weird way, very, very simple. This thing does not have lots of unitary representations. You know, up to this problem, it has only one unitary representation, but it's infinite dimensional, which makes it hard to understand. But what makes it, the good thing about it is that it's exactly the whole formalism that you've gone through, that you go through to talk about a quantum particle. So so this is kind of the end of the story about Heisenberg, Lie algebra, Heisenberg Lie group, and its representation. So any questions about this stuff, about any of those? Okay, so if not, what we're going to do is we're going to go on to the next part of what I want to do today, and so maybe to say a bit about where I'll say a bit about where we're trying to go, and let me just say it in words, then I'll get started on it. So what I want to do today is get started on introducing. There's another kind of fundamental group in the subject, and it's called the symplectic group. And I want to kind of explain the story behind that. And again, the story behind it. Again, I'm going to start by introducing a certain. I'm going to think of it at the Lie algebra level, and I'm going to start by explaining, again, motivating it by some physics, by the physics of Hamiltonian mechanics. So that's what we'll start now is Hamiltonian. So end of this story, and now, but I'm going to start doing something different, but watch for a new Lie algebra and a new Lie group to appear. And then the interesting thing about this new Lie algebra, this new Lie group, is going to be that it's represented on the same space we've already talked about. That it's going to tell us something new about quantum mechanics about canonical quantization. Okay, so let me first say something about Hamiltonian mechanics. So if you take a class in the physics department on classical mechanics, they'll tell you that there are various different kind of formalisms for developing, I mean, at the end of the day, the way you're going to describe some classical mechanical system is typically with some differential equation or some set of differential equations. And there's some which describe them, and the whole kind of package of how you get such things as various forms. One form is starting with the Lagrangian, and then getting all the Lagrange equations. But another form is this form, the form of Hamiltonian mechanics. And this is the form which has a lot of the same mathematical structures that we're interested in. Okay, so here so you can think of this as being kind of. You can start with it thinking about this axiomatically, the same way you think about quantum mechanics at the beginning axiomatically. So the axioms are: one is that the state of a system at some time t is given by to a point in R2D. Okay. So again, this should start to look familiar. It's going to be the same R2D that we're going to use in quantum mechanics. But this is often called phase space. So when I say phase space, I mean an even dimensional real vector space. And the idea, and Hamiltonian mechanics says if you want to characterize, the way to characterize the state of a classical physical system at a fixed time is by points in this phase space. And the phase space is almost, in general, is almost by definition, it's the space of initial data for all possible trajectories of whatever your equations are. But then, so that's the state, and this is kind of vaguely analogous to the axiom in quantum mechanics that the state of a system was given by a vector in vector in some complex vector space. But now, then the observables are functions, and we're going to often choose coordinates Q1 up to Qj and Qd and P1 up to Pd. Okay. So our coordinates are often going to be broken up into dq coordinates and dp coordinates. Functions on rd, r2d, or so if you like, so some function of q1 up to qd, p1 up to pd. Okay, so the observables of your classical mechanical system are just kind of functions of q, some function you built out of q's and p's. Okay, and then 3, there's a distinguished observable. Called the Hamiltonian. I'll write it small h. So small h is just some function of the q's and p's. Okay, and then the dynamics is given by then the analog of Schrodinger's equation is given by the dynamics is given by Hamilton's equations. And these say that qj dot, that the time rate of change of the qj's is going to be the partial derivative of h with respect to the pj's, and the time derivative of the pj's will be minus the h pqj. And you can see that then, and then if you take for a classical particle, will be h is just p squared over 2m plus v of q. Okay. And I've written this just down just for 1 degree of freedom, but you can figure out what it's going to be for arbitrary degrees of freedom. But then if you see what these equations tell you for this choice of h, they just give you the standard, Newton's second law, F is equal to ma, and all the stuff you're used to about classical mechanics. Okay. So now so this is the standard story. But now what we want to do, so what I want to do, so what then happens when you start to do Hamiltonian mechanics is that you sooner or later realize that what's interesting about this R2D is that it comes with some kind of with an interesting extra structure, and that extra structure is normally written down by physicists in terms of what's called the Poisson bracket. So the next, once you have this set up, what you want to do is is you realize this is all going to be a story about functions on R2D, but there's an interesting there's an interesting structure on functions on R2D, which is the Poisson bracket. So a new important structure. Is the Poisson bracket. And what this says is that if you have the definition is then given by, so you write it with a standard thing to do is to write it with a curly bracket, and if you have one function of the Q's and P's and another function of the Q's and P's, what you do is you produce a third function of the Q's and P's by this kind of funny formula by taking is equal to 1 to D, df1 dq, let me j, I guess, j, df2 dpj minus df1 dpj. Anyway, so what this gadget is doing is this is giving you you feed these two functions on R2D, you get a third function on R2D, and the properties are that one f1, f2. Is that you can see that if you interchange f1 and f2, you can just pick up a minus sign. F2, f1. So that's easy to see. With a little bit more work, you can show that it all satisfies the Jacobi identity. Which one way of writing it is just that f1 with f2, f3, and if you take all cyclic permutations of these three things plus cyclic, it sums to 0. So that's a bit more work to show, but you can show that. Okay, but then the thing to realize, and actually, so historically, people were doing this before they knew about Lie groups and Lie algebras. And actually, it's interesting that the first examples of actually Lie groups and Lie algebras kind of came from the fact that people were looking at this Lie bracket and the properties that it had, and they said, wait a minute, those provide a really interesting structure. And so maybe the thing to say here is that this is what this implied. Is that the functions on R2D are a Lie algebra with this Lie bracket. Okay, so this is something which you're not normally told in a classical mechanics class, but but this is true. So the problem with the algebra point of view here is that all the Lie algebras that you've seen so far are they're finite dimensional vector spaces. They're what we call finite dimensional Lie algebras. They can be written as as elements of some finite dimensional. So here the problem is this is infinite dimensional. So the fact that you've got an infinite dimensional Lie algebra now all of a sudden you've got a you've got a much trickier set of problems of what to do, of how to deal with it. You can't, the kind of definition that I gave you guys, that the way to find a, that something was a Lie algebra if you could, if it was a bunch of matrices that you could exponentiate to get a matrix group. That's not going to work. These things are not, the space of functions is not a it's not a nice finite dimensional space. You can't kind of identify these functions with matrices in any simple way. And you could, if you want, try and say, well, the Lie group is going to be the thing whose derivative at the identity is this infinite dimensional space, but it's also going to be an infinite dimensional group. And so I'm going to use this. I'm going to use the fact that the Poisson bracket structure gives you a Lie algebra structure. But we're not actually going to use the Lie group very much. Maybe let's just say it. Let me just say this in words. Then, I mean, there is a Lie group behind all this, and the Lie group is basically the it's basically the group of all. It's basically the group of all. Of all C infinity isomorphisms of R2D with itself that preserve the Poisson bracket. That when if you do some nonlinear change of coordinates on R2D, and when it doesn't change, and when you do that transformation to the functions, it doesn't change the bracket of the functions. It preserves this bracket structure. Then the group of all such gadgets is your group. And these things have a name in mathematics called symplectomorphisms, which I may say a little bit more about. But we're not actually going to work with that infinite dimensional group, and we're not going to work very much with this infinite dimensional Lie algebra. But there is an infinite dimensional Lie algebra behind, and if you look at a lot of the manipulations going on in a Hamiltonian mechanics book, a lot of them are really exploiting the fact that you've got a Lie algebra. And to give the story away in some sense, the what's gonna happen is the point of view of the relation of this to quantum mechanics, which is kind of what Dirac realized. I mean, Dirac, when he saw the Heisenberg commutation relations, he said, "Wait a minute, I've seen commutation relations that look like that before, and in my classical mechanics class." And so in some sense, Dirac's idea about quantization is just that if you want to think about how to get what quantum mechanics is really just classical mechanics is about this Lie algebra. Quantum mechanics is about the a unitary representation of this Lie algebra. But we're going to see that there's a problem with all this. And, we're trying to think that way. Okay, so let me see. Okay. So now,
Professor?
Yeah.
Just to be clear, we're imposing some kind of condition on the functions, right? We're not just talking about the general function space over R2D.
I mean, this is kind of very. I haven't actually thought. I mean, actually, in practice, what I'm going to actually do, the computations we're going to do, they're always going to be polynomial functions.
Okay.
But you could look at more. You could try to look at a more. I mean, this does make sense for more general classes of functions, but yeah. I mean, this is an infinitesimal space, and exactly which infinitesimal space, I don't want to. Yeah. That's a hard question. But you can definitely make sense of this for polynomial functions, and you can do it for more general functions. But then you have to get into all sorts of things which aren't too relevant to what we're trying to do. Okay. And then but then maybe just the last thing that I didn't. Okay. So let's talk about some properties of this Poisson bracket. So in terms of so you have one thing to say is that Hamilton's equations are well, or actually more generally, you know, let's say this generalized to if you got some function of some observable, and if you want to know how the value of the observable is going to change as your system evolves in time, what you do is you compute the FDT. What you do is compute the Poisson bracket of that function with the Hamiltonian function, and that will give you that will give you the change. So this is the classical mechanical analog of the Schrödinger equation, if you like. This is how dynamics works, and that the H, you know, if you think of these functions as being in the Lie algebra, that this is kind of telling you that the way that this Lie algebra kind of evolves under these Lie algebra observables that evolve under time is through the Lie bracket this way, through Lie bracket. This is giving you the infinitesimal change of an observable. Anyway, let me and then but there's something at the just so the linear functions, the basis of the constant function 1 and the QJs and the PJs. Okay, so linear functions on R2D are given by these things, and these have a Heisenberg they give a subalgebra of the Lie algebra of all functions algebra, because you know, QJ QK is equal to PJ PK is equal to 0, and QJ PK is equal to delta JK plus 1, and then one commutes with everything. Okay, so this is the you know, this is isomorphic to the Heisenberg subalgebra. So you normally think of the Heisenberg algebra as something very quantum mechanical, and it's something that you only see once you start thinking about quantum mechanics. Well, if you just think about if you just do Hamiltonian, if you just do Hamiltonian mechanics, then you stick to just looking at linear functions. If you simplify to this very, very simple case of linear functions, well, then the story is about the Heisenberg algebra. I mean, that's not so this is not very interesting in classical mechanics, but the algebra is already there. Okay. Okay. So now let me try to, the last part of this, explain kind of where the next part of this, where we want to go with this. And again, I'm skipping over. There's a lot of stuff in the book about symplectic geometry and about the relationship between symplectic geometry and Hamiltonian mechanics. And if you've seen a lot of Hamiltonian mechanics, you might find this readable, or if you've seen a bunch of geometry, you might find it readable. But unless you're have some significant background with both of those, some or both of those, this is maybe hard to follow. But let me say this. So let me do the next thing. Okay, where I'm going with this, I guess, is that so the next topic is that the quadratic polynomials in P, QJ, J also give a subalgebra. And so what if you start playing around with what this Poisson bracket does on polynomials, what you find is that if you Poisson bracket together two order 1 things, you get something, or you get 0, or you get something order 0. If you put together something that's order 2, Okay. So if you take any kind of polynomial with just things of second order, and you put together, if you bracket it with any other function of the q's and j's of second order, you're going to get a third thing of second order. And the number of polynomials of second order is some nice, they're just a nice finite dimensional vector space of such things. And so this actually gives you another interesting subalgebra of this infinite dimensional algebra. So what do you get? So we need to say that. So you get the order 2 polys in like the q vector or the p vector coordinates give a finite dimensional the algebra, inside the infinite dimensional. So what we did. So what I was kind of arguing is that a good way to think about classical Hamiltonian mechanics was that there was an infinite dimensional Lie algebra there of all functions, or maybe just polynomial functions on the phase space. But the problem with that is that that's infinite dimensional, and the theory of kind of infinite dimensional Lie algebras or representations of infinite dimensional Lie algebras is very, very difficult and very complicated. Whereas finite dimensional Lie algebras we can actually say a lot about. So the Heisenberg Lie algebra, linear stuff was one subalgebra, but the order 2 things give you another finite dimensional Lie algebra. And this is called, and maybe I should also explain that things then stop here, because if you take something of order bigger than 2, anyway, if you start bracketing together things of order bigger than 2, what happens is you end up the bracket increases the order, and so if you try and make a bigger subalgebra than the ones I'm talking about, you're going to run into trouble that this relation is not going to close. That you're going to, if you had some nice finite dimensional subset of the things, if you bracketed them together, you would go out of the subset and you get into something bigger. So the only really interesting finite dimensional subalgebras are the Heisenberg subalgebra, which we already know about, and then this one. And this one has a name, so this is called the Lie algebra of the symplectic group. So again, I've done something. We'll give it a. The notation for it I'll put is SP for symplectic 2D, because we have to get D in there somewhere, and then let me just put an R here to distinguish it from other kinds of SP groups. Okay, so again, I've told you actually quite explicitly what the Lie algebra is, but I haven't told you I haven't told you how to think about the Lie group. I mean, if you want, what I'm going to do later, and what I do in chapter 16 is I actually find so chapter 16 or 16, I spent a lot of time working out you get an explicit matrix, a realization of this Lie algebra. So I get an identification of these order 2 polynomials with matrices of a certain size, and so that the Lie bracket is given by the Lie bracket of matrices, and then exponentiating those things, I get a group, which is a symplectic group. And so you can exponentiate, right, and get the group. So one kind of very kind of not so easy to understand way of defining this group would be to start with the Lie algebra, exponentiate, and look at the group of matrices you get. But maybe so what's in these chapters, I should say, what's really going on in these chapters is trying to get to do that calculation, but to do it in the context to try to explain a bit more about what this group really is, about how you really should think about this group. And the idea is really this. So let me so a better definition. Of SP then 2D R would be this, is that, so recall, let's recall that if somebody is that, if somebody gives you, so given Rn, the standard is a positive, definite, non-degenerate bilinear form. Okay. So one of the standard things that, in some sense, is a standard kind of theorem of linear algebra is that if somebody gives you somebody hands you a vector space and they give you a bilinear form on it that's non-degenerate and positive definite, that you can find coordinates that you can put it in the standard form, in the standard diagonal form. You can diagonalize this. You can diagonalize this quadratic form. You can put in and you can put in the standard form, and there exists. So the group. And so this is just this is just the inner product. The group preserving the inner product is the orthogonal group. And we talked a lot about that already. But now what you want to do is so now you're given. So what really what we want to do is we want to we want to just change. Oh, sorry. I think I missed something here. I should have said symmetric. So what we want to do is we want to change. What if we change symmetric to anti-symmetric? So this is in some sense the idea. So this is what's normally called Euclidean geometry. It's the geometry associated with the symmetric inner product here. What we're going to be doing is, in some sense, trying to take everything we know about Euclidean geometry and the orthogonal group and change things around to the case where you've got an antisymmetric bilinear form. So given omega, okay. So so one thing that happens is that if you try and do this, if you try and put an antisymmetric bilinear form on an odd-dimensional vector space, you can show that it has to be zero. You can't get a non-degenerate one. So what we're going to do is, given omega an antisymmetric metric non-degenerate antisymmetric non-degenerate bilinear form on R2D. And I think I should say something about the positivity condition you need, but let me not think about it. I don't. Anyway, that isn't really relevant right now. But let's just say, but again, there's going to be, just like there's a standard one of these, which is the diagonal thing. Here, there's going to be there's a standard antisymmetric thing where you just have, you have something on. You have something on the upper triangular part of the matrix, and then minus the same thing on the other, reflecting about the diagonal. And if you take, so you can always put such things in that kind of standard form, and then there's a group preserving this. Is SP up to. So there's kind of there's a general kind of geometric characterization of this group is as not as an analog of the group preserving a standard inner product, or the group preserving a standard symmetric bilinear form. This is the group preserving a standard antisymmetric bilinear form. Okay. And the simple, maybe let me just say quickly before stopping, give you the simplest example. It's basically D is equal to 1. And so then omega of, if you feed it a vector, how did I want to write it down? X1, something with coordinates x1, y1, and coordinates x2, y2, then you're gonna get the thing that you write. Well, you get x1, y2 minus y2, y minus y1, x2, which you can write x1, y1, 0, 1, minus 1, 0, x2, y2. So in D is equal to 1, there's really kind of, up to a scalar, there's really only one such gadget, and there's only one non-degenerate bilinear and antisymmetric bilinear form. It's this guy, and you can write it in terms of matrix multiplications this way. And so you can characterize the group elements the things that preserve this. This are G. So let's write them as G alpha. They're two by two real groups of real matrices, such that G. So if you act on here then take a transpose, and then multiply by 0, 1, minus 1, 0. And then on here, you should get back the same thing. Okay. Okay. So what you can do is you can work out, plug this formula into this equation and see what condition you get on the 4 real numbers alpha, beta, gamma, and you'll see that what you get is you get that the determinant G is equal to 1. And so what you find is that SP of QR is the group of it's all linear, real 2x2 transformations with determinant 1. And that's the group that we've been calling SL of QR. Okay, and so I better stop here. But where this is going, and what I want to kind of motivation for a lot of this is to introduce these besides the Heisenberg group, introduce this new class of groups, the symplectic group. And the first example of these guys is is a group that at least in principle you've always heard of. It's a 3-dimensional Lie group. It's non-compact. It's a fairly tricky thing to think about, but it's this guy, and then these guys for arbitrary D, you get bigger things. You get a whole class of groups, and the idea is going to be that these groups are going to act. These are going to kind of contain all of these groups are the things. Are the biggest group the biggest groups of transformations that preserve the notion of what a Poisson bracket is, and they preserve this underlying Lie algebra structure. Anyway, they preserve the algebra structure at a linear level, and so our arbitrary groups of transformations that that we're interested in are going to sit inside these groups. So what I'm going to do is I'm going to be spending a lot of time thinking about these general groups and working out what they do, because they're really kind of a general case, that they're really the things, all of the symmetries of our classical mechanical system and later of our quantum mechanical system are going to come about because are going to appear as subgroups of these guys. And so we want to develop some technology for working with those. And so that's where this is going. And again, apologies for these few chapters. If you try and read them, you'll see that what I told you about today is some of what's in chapter 14 and started about some of what's in chapter 16, kind of skipping a lot of the stuff about geometry. And what I'll do after we come back at next week and next Thursday is go back and do some of the geometry and then work through some more of the details of this so that you actually have enough, you can actually do computations with it. Okay, so any questions now, or you're welcome to come back and talk a little bit later. Also, just so there's no class on Tuesday because of election day. So I'll see you again in a week. But anyway, like everybody else in the world, I think I would love to go on vacation and use this opportunity to travel and go somewhere else, but I can't. So I'm around. I'm here. Anybody who, if you have some questions about any of this, feel free to contact me over the next week. I'll be around. Happy to connect. We can talk about it. Okay. Okay. So anyway, if I don't see you before that, I'll see you all next Thursday, and have a good break, whatever you can make of it. Okay. Bye.
Thank you. Bye.
Bye.
Thank you.